In this lecture, we are going to talk about the classification of differential equations. So classification of differential equations. Classification of differential equations. There are many types of differential equations. So there are many types. There are many types of differential equations. There are many types. There are many types of differential equations. So let's start with the one that we already know. So what we call the ordinary differential equations. Ordinary differential equations. Ordinary differential equations. We normally call this ODE. Ordinary differential equations. Ordinary differential equations. So what are they? So in ordinary differential equation, there is only one independent variable. So there is only one independent variable. There is only one. There is only one independent variable. Independent. There is only one independent variable. So that's the major property. And so we can say derivatives are taken with respect to that variable, and the derivatives are taken with respect to, we normally write w dot r dot t. Maybe you learned that in calculus 1. So we normally call this with respect to. Okay, we call w dot r dot t with respect to that variable. So what we're gonna see? We're gonna see things like so for example, we're gonna see so let's look at some examples like that. So examples. So it is a dy over dt equal ky. So this is the exponential growth model. Exponential growth model. If k is negative, this is going to be the exponential decay model. Okay, and then we can also talk about, so we assume that k positive, that's why we say growth. And then we have dy by dt equal k a minus y. So this is you have seen this in physics. So this is the Newton's law of cooling. Newton's law of cooling. Newton's cooling law. So that's a differential equation. Dy by dt equal k times a minus y. So this is also this exponential decay model actually. So the exponential decay model, decay type, let's say type, because there's a shift here, a minus y. Okay, and then we have this one. This is the m d squared x over dt squared plus c dx over dt plus kx equal ft. So we're going to learn this equation in a future lecture. So this is what we call the mechanical vibration. Mechanical vibration. Okay. Mechanical vibration. So I'm going to say we'll learn later. we'll learn later. We're gonna analyze this equation a lot. Okay, we're gonna consider different cases. What happened with C, 0, positive C, negative C, K, positive, negative, stuff like that. Okay, and also FT, negative, positive. Okay, so those are kind of several ordinary differential equations, and you're gonna see all of them. Maybe you have already seen some of them in your other classes. Yeah, and but we're gonna solve all these equations in this class. We already solved the first one, but we're gonna learn a approach to solve these kind of equations later. That's the first type, what we call the ordinary differential equations. So let's go to the second type. The second type is what we call the partial differential equations. Partial differential equations. That's the next type. So I'm going to say type 2. Yeah. So let's say type 2. Okay, type 2. So this is a partial differential equation. Type 2 partial differential equations. Partial differential equations. Partial differential equations, or what we call PDE. Partial differential equations. So what is a partial differential equation? When you talk about partial differential equations, not like in ordinary differential equation. In the ordinary differential equation, we had only one independent variable. Here we have several independent variables. Several. That's a major difference. Several independent variables. Several independent variables. That's a major difference. Several independent variables, and we can say the equation depend on the partial derivatives of the variables. Okay, so the equation depends on partial derivatives of those variables. Okay, of those variables, partial derivatives of those variables. So it's a partial derivatives. So if you are not familiar with what we mean by partial derivatives, let's kind of have a look at it. Let's try to understand what we mean by a partial derivative. So I'm going to kind of have a little digress from what we are talking about. So let's talk about what we mean by partial derivative. So what's a partial derivative? So this is something we learn in Calc 3. So if you did not take that class, so let's talk about a little bit about that. So what is a partial derivative? What is a partial derivative? What is a partial derivative? Okay, what is a partial derivative? So when you talk about partial derivatives, what we can do, basically, because there are a lot of variables. Now the question is which one you're going to change. So you can't change everything at the same time. So instead, what we're going to do, we can change only one variable and keep everything else fixed. Okay, it's a kind of interesting idea. So we're going to keep all the variables fixed, except one. Okay, except one. So that's the interesting part, except one, and that one, like, just consider as a regular derivative, just one variable situation. So it's not that bad. Okay, you can see, like, it's not that difficult. So consider as, okay, we can say consider as the only independent variable. Consider as the only independent variable. Only independent variable. Okay, so we just take a regular derivative considering everything else is fixed. Okay, so let's talk about some notations. So what notations we have? So we have some notations. So we basically use two notations actually. Notations. So there's a letter we can use for that. So this is what we call dabba. So dabba u over dabba t. So let's say your independent variable is t. So here the t is the independent variable. Okay. So we're gonna say so independent variable. So independent variable. So when you have this one, this means that all the other variables are fixed except the time variable. Okay. So this means that, so let's write it. So this means that all the variables except t, all the variables except t fixed, all the variables except t fixed. So we're gonna, so except t, we're gonna consider everything else is fixed. Okay. So let's look at another one. So when we write like this, so dabba u over dabba x. So how we read this? So we can read this as, so read as dabba d-a-b-a dabba u over, or you can say by, okay, dabba u over dabba x, dabba u over dabba x. So that's how you read it, dabba u over dabba x. The first one, dabba u over dabba t. Okay, so let's look at some examples. So I mean, that's it. Look, what you want to do, you just keep all the other variables fixed except the one in the bottom. Okay, you keep all the other variables fixed except the one in the bottom. So so let's look at this example. So how about this one? So let's say the first one, I'm going to say u, let's assume that u is a function of two variables just to make things easy. It can be any number of variables, it doesn't matter. So let's say there are two variables. So let's say x and a t, those are two variables. Let's say this is your function. So it's more than one variable now. Okay, 3x squared plus t plus 3. So that's your function. Now let's start at the derivative. So what we're trying to do, let's look at this one. Let's look at dabba u over dabba x. So what is this? This means that so there are two variables. X is in the bottom, that means t is fixed. Okay, meaning that act as a constant. Okay, so you can treat the t term just like a constant. So that means if it's a constant, if you try to take a derivative of that with respect to x, it's going to be 0 because you treat t as a constant. So that means so what you're going to get is, so dabba u over dabba x is, so only x is the variable. So it is just take the regular derivative. So if you take the derivative, it's going to be 6x. So t is a constant, so it's 0. 3 is also constant, 0. So you only get 6x. So that is a partial derivative of u with respect to x. So let's do the same thing. How about this one? How about dabba u over dabba t? What does that mean? X is constant. The other variables are constant. So x is fixed or x is constant. You can treat, okay, it's not a constant, but you can treat it like that. So that means you're going to get dabba u over dabba t equal, so x is a constant, so it's 0. T, that means 1. 3 is a constant, so you get 1. Okay, so you can see it's not that bad. Okay, so that's what you get. So it is 6x and 1. So let's do one more example. So how about this one? So u x t equal 3x squared t plus 2x cube plus t minus 2. So let's do the x partial derivative. So dou by u over dou by x. So that means the t is a constant, so t acts as a constant. So if t is a constant, this is a product, t is just a constant, so we take the derivative of the x term. So you're going to get 6x, but t is a constant, so you just rewrite. Now so x, so it is 6x squared, t is a constant, so 0 and a 0. So you simply end up getting 6xt plus 6x squared. How about dou by u over dou by t? So we have, so now x is a constant. So if x is a constant, we get 3x squared, derivative of t is 1. Okay, so you can write 1 if you want. And then, so x is a constant, so 0. T is a 1 minus 2. So that means you're going to get 3x squared. Actually, what happened? Yeah, this is 0. Okay, so plus 1. Plus, it's not 2, plus 1. So, so those two are the partial derivatives. Okay, now, so these are the first derivatives. So what if, like, you want to take multiple derivatives, like higher order derivatives, second order derivatives, third order derivatives. So it is not like in the regular case, because in the regular case you're going to get d squared u over dx squared, d squared d cube u over d x cube. But now we have two variables, so that means we don't know which one gonna happen first. So that means there's something else happen here, like there's a notational thing here. So let's look at that now. So let's say higher order derivatives, higher order partial derivatives, okay, higher order partial derivatives. So what we do, it's just the same thing. We're gonna just do the same way as we do in the regular case. Okay, so do as we did in the classical case. That means just do the same thing as we do in the regular with regular derivatives. So for example, so what we mean by that, so we know that when you have d squared y over dx squared, what does that mean? This means that the derivative of dy over dx, is that right? D squared y over dx squared means d over dx of dy by dx. So we do the same thing here. So that means what we do, dou by square u over dou by x squared, this is simply equals to dou by over dou by x of dou by u over dou by x. Okay, so if you go with the previous example, this means that dou by over dou by x, so what was the du by dx? The du by dx was 6xt plus 6x squared. That's what we get. Now what we can do, we can take the x partial derivative of this. So what's x partial derivative means? T is a constant. So if t is a constant, so you're gonna get 6. You're gonna get the x partial derivative. So that means you're gonna get 6t because t is a constant. It's a product. So you take the derivative of x as 1. So 6t plus you're gonna get 12x. Okay, so x is a variable. So how about this one? How about dou by squared u over dou by t squared? So it is as before, dou by over dou by t of dou by over dou by u over dou by t. So this is dou by over dou by t, dou by u over dou by t, it is 3x squared plus 1 that we get. So we can take with respect to t, but x is a constant. That means this is simply a constant. You get 0. Yep, surprising, but you get 0 because it's a partial derivative with respect to t. And then we have da by squared u over da by x da by t. Yeah, we have like weird one now, because now we have two variables, so it's not like before. It's not like in a regular case. You have to write it like that, da by u, da by x. So which one comes first? So we start with u and try to go away. So this means that da by over da by x of da by u over da by t. That's what it means. Okay. Yeah, so we go that way. So that means it's a da by over da by x, da by u over da by t. We already have it, is 3x squared plus 1. One should now is it the x derivative. That means you're going to get 6x. Okay. Good. And how about one more? How about we change the order? Da by t, da by x. What does that mean? That means da by over da by t of da by u over da by x, and sorry, da by over da by t. Da by u over da by x is 6xt plus 6x squared. So we take with respect to t, so you're going to get 6 with respect to t. So it's a t, that means you get 1. X is a constant, so 6x plus 0. Okay. What do you notice? You notice that this and that are the same. You see that? These two are the same. So that means this is a general result actually. So so we're going to say notice that. Okay, notice that da by squared u over da by x da by t is exactly equals to da by squared u over da by t da by x. So what we normally say, the mixed partial derivatives are equal. This doesn't happen always. So we normally call this mixed partial derivatives. Mixed partial derivatives are equal. But this doesn't happen in general. Okay. But we also need this later. This is one of the results that we can use. So these kind of functions, like what we call smooth functions. Smooth functions satisfy this condition. Okay, so this need later. Need later when we talk about the uniqueness. Okay, need later. And also few things. So work for smooth function. Work for smooth. Okay, work for smooth functions. So doesn't happen in general. Not happen in general. Not happen in general. So it doesn't work in general, but for a smooth function, we see this. We see that the mixed partial derivatives are equal. Okay, there are some other notations as well, so let's talk about that now. Other notations. Okay, other notations. So what are other notations? We normally write, because there are a lot of writing here. When you want to write it like that, da by x squared is a lot of writing. Instead, we can write u. We put just small subscript. We can say x and x, two partial derivatives. So that's the notation we use. And then, but what if you have mixed derivative, like da by squared u over, let's say, da by x da by t. So we know that this is da by x and then da by u da by t. So which one you do first? So you know that this is the first one, right? That's the first one, that's the second one. Order matters in general, okay? So that's the first and second. So that means because of that, we can write this one as u. Which one you do first? You do the t first, and then x. So we write utx. T comes first. So you start with u and try to go out. So we write it like that. Okay. So this one we go this way. So that's the order. Good. So let's try a few more notations. What about double squared u over double t squared? So this is, we can write a u t t, right? Another mixed derivative, double squared u over double t double x. So this is double over double t of double u over double x. So that means the notation would be you do x first and then t. But as we discussed before, they are the same for smooth function, so they equal. So same for smooth function. Okay, same for smooth function. So that means for some most of the function that that you can see in a regular basis, you're gonna see that uxt equal utx, but you can easily find some function that that this result doesn't work. Okay, yeah, so it's only for smooth functions. Good. So now I will give you like this one for you to practice in a little bit more. So I'm going to call this exercise. So let's say the first one, find uxx, uxt, utx, utt of these three, uxt equal x plus t, b uxt equal x squared minus xt plus 3, and then c uxt equal x over t. Yeah, be careful, you have to use the quotient rule for that. And number 2, find vxx, vxy, and then vyy, and then vyt, and vxyt. Oh, we have 3 now. So it's the same thing, you just have one more variable. Start with x, y, and then t. Okay, so in that order. Okay, but this is a function, so I'm going to call this d. So vxyt equal x, y, t plus x squared plus y cube minus t to the 4th. You're going to see this kind of function if you take some class in physics. If you talk about relativity theory, you're going to get these kind of things. Talk about hyperbolic spaces. Okay, so the answers. So answers to this goes to the description. In the description. Okay, so look at the description. You can see the answers for those questions. Good. So this is just a kind of basic introduction of partial derivatives, and we are not going to use much in this class. we hardly see them in this class because this is partial differential equation is the next level, so we can talk about that in a different class. Okay, good. So let's come back to what we are doing. Okay, we only like trying to learn about classification, but I need to talk about some partial differential equations. So but you need to have some idea about that. Okay, but that's just a different class. You learn some partial derivatives in Calc 3. So let's go back to what we were discussing. So now let's talk about examples. So we're gonna come back to what we were discussing. Okay, so examples of PDEs. Examples of partial differential equations. So for example, if so we have, let's say, dabba y over dabba t plus c dabba y over dabba x equal 0. Okay, so this is what we normally call the transport equation. Transport equation. Transport equation. So like if there's a flow, so what we're gonna do is we're gonna measure the, let's say, you can pick some quantities like, let's say, density, a mass, or something like that. So let's say we're gonna see what happened at the x position and the t time. So time t equal t, at the t time x position, what's the density, something like that. So we're gonna measure y, so maybe y, maybe the density. Okay, so this is what we normally call the transport equation. So it says that 0. So here y, in this y is a two variable function. So this y is a two variable function. So it is x and a t, and it's a density, but it's a two variable, or the concentration. Okay, so it's a two variable function. Y is a two variable x and t. So let's see more examples. We have dabba u over dabba t equal dabba squared u over dabba x squared. So this is what we call the heat equation, okay, or diffusion equation. So the heat equation. So you can see transport equation, heat equation, and then the wave equation. So it's dabba squared u over dabba t squared equal dabba squared u over dabba x squared plus dabba squared u over dabba y squared. So this is what we call the 2D wave equation. So you can see that all those are all major equations. Because of the wave equation, we're gonna hear. Because of the heat equation, we're gonna maintain our body temperature. Because of the transport equation, all the blood and everything gonna flow through the body because of transport equation. So you can see that all these equations are very important in the nature, and but they are all partial differential equations. Okay, it's very interesting. Okay, so the next type, so these are some of the examples of partial differential equations. Okay, so it's a transport equation, heat equation, and the wave equation, 2D wave equation. So you can have a 3D wave equation. You have one more variable, you have a z variable, but this is 2D. And then so the next topic is the system of ODEs. System. Okay, so we kind of try to learn some terms here. So system of ODEs. System of ODEs. So what's a system? System means it's not just one equation, but you have several equations coupled together. Okay, so several couples ODEs. Okay, ODEs depend on each other. Several coupled ODEs. In other words, couple means depend on each other. Okay, so depends on each other. So it will be clear, like for example, let's say y prime, that's a y derivative is a function of x plus 1. Let's say x derivative is a function of, let's say, y minus xy squared. You can see that the x derivative depend on y derivative depend on x, the x derivative depend on y. So this is a kind of situation what we call a system of equations. Sometimes, you know, we just write it like that. We're going to put like a curly brace like that to mean that it is a system. It is a system. Okay, that's a kind of notation, but sometimes we even ignore that. So that's not a big thing. Okay, so that's the next one, is a system of ODs. So similarly, we can have system of PDs also. Okay, so yeah, so let's talk about that system of PDs. So same idea. Okay, so same idea. So the system of partial differential equations, same idea. So again, so you can say coupled PDs. Okay, so coupled PDEs. Okay, coupled PDEs. One good example, like, you know, everyone used that, like, you know, your cell phone and radio, TV, everything use this, what we call the electromagnetic equations. Okay, the Maxwell's equations. So so Maxwell's equations of electromagnetic theory. Electromagnetic theory. So for example, so this is a system, but I'm not gonna explain much because this is not a physics class. I just write it just to give you an example, so you might not be able to understand what I'm talking about, but that's okay, because it can take too much time if I want to go. But this just, I want to tell you that there are things like that. Okay, so this is what we call the del dot. It's called del dot d, the vector, equal rho, and then del dot b. B is a magnetic field, equal to 0, and then we have the what we call the curl. So del and the cross. Okay, E, electromagnetic field, equal negative delta b over delta t, and this b is a vector. And then we have del, this is again curl h, equal j plus delta d over delta t. So these are what we call the system of equations. These are called Maxwell's equations. So it's again a system, so they work together. So the first one is the dot product that you learn in Calc 3, the dot product. So this is a dot, and the next one is also a dot, and then the curl. Okay, the cross product. So this is a dot product, and here the cross product. The last one is also the cross product. You don't want to remember those things. Okay, this is physics, but I want to tell you what is out there. Okay, what is out there. So you might be learning those things later if you take advanced physics classes. These are called Maxwell's equations. Okay, but I want to tell you this is a system of PDEs. Okay, you don't want to remember this one for this class. This is just to tell you that what's out there. So and there's a definition for the this is what I call the del operator. So it normally write as delta over delta x I plus delta over delta y j plus delta over delta z k. So this is the definition, and then you can take the dot product. It's very easy after we do that. So you can see that the partial derivatives appear there. So those are the partial derivatives that we just talked about. Okay, so this is one of the applications of partial derivatives. You see, it's there. Okay, partial derivatives. Partial derivatives, and then we have what else we have? We have the del. So this is what we normally call the divergence operator. Del with a dot is called a divergence operator. divergence, and then we have this, that what we call the curl operator, curl operator, divergence and the curl. But in this class we don't do much with these. Okay, maybe this is the only time we discuss this for this class. Okay, so I want to tell you that because you might get scared what we are trying to do. Okay, so but this is like if you plan to do physics, you definitely gonna see these things again and again. Okay, later. So I want to tell you that we do not do much. Okay, so we don't do much with this okay, this in this course, okay, so that's for physics. Okay, what's the next important type, what we call the order of an equation, order. Okay, order of an equation, order of an equation. So what's the order of an equation or a system, So what's the order? Order means the highest derivative. Okay, so that's the order of the order of an equation is the order of the highest derivative, order of the highest, order of the, we can say largest. Okay, largest derivative appears. Large order of the largest derivative appear. Okay, appeared. So so let's look at several examples. So how about dy by dt equal k a minus y. This is the Newton's law of cooling. So you can see that it's a differential equation. You can see that the largest derivative appears the first derivative, so we call this is the first order differential equation. First order differential equation. So how about this one? How about m d squared x over dt squared plus c dx over dt plus kx equal ft. So you can see that the largest derivative appears a second derivative. That's the largest derivative, so it's a second derivative. So that means, so this is second order. So this is a second order differential equation. So second order differential equation. So those are ordinary differential equation. What about the partial differential equation? Let's look at a partial differential equation. Okay, so the first one is first order because it's the largest derivative, the first derivative. In the second one, oh actually it's not daba, it's d. Okay, this is a mechanical vibration we discussed earlier. So you can see the largest derivative appears is a second derivative, so it is a second order differential equation. So let's look at the situation of a partial derivative. So so this is useful in engineering. It is a to the fourth power dabba 4y over dabba x4 plus dabba squared y over dabba t squared equal 0. So you can see it's a partial differential equation. The largest derivative appears is a fourth derivative, so this is a fourth order PD. Actually we're gonna solve this later. Great. Oh no, actually yeah, so not in this class. Okay, so we can solve this in this class. This is a different type of problem, so but we're gonna solve this in applied PD class. Okay, so this is what we call the transversal vibration of beam. Like, so let's say you have a beam, so you kind of clamp on the wall, two sides like a concrete beam. So then what is the vibration in this way? So that is called vibration. Okay, so this is what we call the transversal vibration. Okay, transversal vibration in a beam. Okay, it's going to follow this partial differential equation, but it is a fourth order PDE. Okay, so the next topic is linear equations. Linear equation. So what is a linear equation? We can say an equation is linear if the dependent variable and if the dependent variable or variables, okay, there can be more, or variables, okay, and their derivatives and their derivatives equation linear if the dependent variable and their derivatives appear linearly. Okay, appear linearly. That means the degree of those terms, the power of those terms has to be 1. Okay, that's what it means. So there is only a first power. We can talk about several examples. It will be very, very clear. Okay, first power. So what the power of those terms, power of the dependent variable or the derivatives has to be 1. Okay, so equation linear if the dependent variable and their derivatives appear linearly. That means there can be product here, no products. Okay, so easy way to remember, not multiplied together, and then no other functions. There should be only one. Okay, linear, no other functions, functions of the dependent variable. Okay, no other functions of the dependent variable, no multiplications. And then an equation which is not linear is called nonlinear. An equation which is not linear is called nonlinear equations. Okay, so we can solve some nonlinear equation in this class. Okay, so linear. What is linear means? An equation is linear if the dependent variable and their derivatives appear linearly. Okay, that means they cannot have squared power, square root terms of the derivative, square root terms of y or y cube, y square root, those kind of things you can see. So let's look at several examples and then it will be very clear. Okay, so let's look at several examples. So how about these examples? So let's say 3d squared y over dx squared plus 5 dy over dx minus 3y equals 0. So you can see that the y term and the derivatives, the power of the derivative are all 1. For example, what is the derivative of this? What is the power of this term? It is 1. See that? This is 1. Same thing. The power of this one is 1. Power of this one is 1. So that's what it means. All the powers of those terms has to be 1. So let's look at more examples. How about this one? E to the x d squared y dx squared plus sin x dy over dx plus x squared y equal 1 over x. We only worry about the dependent variable. We don't worry about the independent variable. So since x is the independent variable, this term is okay. This term is okay because it's the independent variable is x. Okay, so x is the independent variable. The y is the dependent variable. So you need to worry about the dependent variable. So you can see that the power of y is 1, or power of y or its derivative is 1. Okay, so that means this is a linear equation. So this is a linear equation. How about more? How about this one? Ex d squared y over dx squared plus sin y dy over dx plus x y squared 1 over x. So linear or non-linear? What do you see here? You can see that this square, so there's a y squared term, so that makes this non-linear. But there are more reasons. You can have this one. See, the y is the dependent variable. You can have sin y, okay, because it is not a linear function, it's a non-linear function. So there are 2 reasons why this is not a linear equation. So this is not linear because of 2 reasons. Okay, so this is one reason, and that's the other reason. Good. How about this one? D squared y over dx squared square root equal x plus 1. You can see that this is non-linear. Why? There's a square root, there's a half power. So this is non-linear. So this is non-linear. But you can easily make this linear. Okay, well, how you make this linear? You square both sides. When you square both sides, this is going to be a linear equation. So sometimes you can do that. Okay, so you can turn non-linear equations to linear equations. So can be made linear by squaring. Okay, so that means if I asked you to solve this equation, that's exactly what you do. You square this first, and then you can integrate twice. Okay, so after that, this just simply become a calc 1 problem. So you first square and then integrate. Good. How about more equations? How about this one? So this is non-linear. How about this one? D squared y over dx squared plus 3x dy over dx. So far it's okay, but I'm going to put a square here. Okay, now it is not. Okay, because of the square term equal 3. So this is non-linear. So this is non-linear. Good. And then how about this one? Dx over dt equal x squared. Linear, non-linear. This is again non-linear because now here the dependent variable is x now. So this is non-linear because it's square term. Okay. So yeah. Okay. So this is non-linear. Okay, this is non-linear. This is a non-linear first order. Okay, non-linear first order. Good. So there's a theory which says that any linear equation, any linear ODE, any linear ODE can be written as in the form, any linear ODE can be written in the form ANX is a function of the independent variable, any function of the independent variable to the nth power of nth derivative of y plus any function of the independent variable n minus 1 power of n minus first derivative of y, like that. Just keep doing it, and then you're gonna get a1x dy over dx plus a naught xy equal a function of b. So any linear equation you can write in this form. Okay, any linear equation can be written in this form. Okay, any linear equation can be written in this form. So it's important. So all those linear equations can be, so you can see that the coefficient are functions of, so these are the coefficients. What are the coefficients? So these are the coefficients. These coefficients are functions of the independent variable. You see that? Function of the independent variable. So any linear equation you can write it in this form. Okay, so this is very useful later. Good. And then so we can say the functions are called the coefficients. The functions are anx, an minus 1x, like that, a naught, are called coefficient functions. Are called coefficient function. Are called the functions anx, an minus 1x, a naught x are called coefficient functions. Good. So good. So let's talk about linear PDEs. Okay, linear PDEs. So linear PDE, the same idea. So for example, if you look at the Maxwell's equations, all the 4 equations are linear. Okay, what you need to do is you need to rewrite those divergence and the curl operators, and then you can see it, but we are not going to do it in this class, but I just mentioned that those are linear. Okay, so what I say, need to write each using partial derivatives. Then you can see that it's linear, but we don't do that in this class. Okay, I just want to mention. And then let's talk about nonlinear PDEs. Nonlinear PDEs. So there are several nonlinear PDEs. There are a lot of applications in nonlinear PDEs. That's just a whole new theory. So for example, Java y over del by t plus y del by y over del by x equal nu del by squared y over del by x squared. So this is what we call the Burger's equation. Okay, so Burger's equation. That's like a physicist in Maryland. Okay, so this is a nonlinear. You can see this is nonlinear because of this term. See, there's a product here. So this is nonlinear. So this is a nonlinear second order PDE. So this is a nonlinear second order PDE. Okay, nonlinear second order. See the second derivative, the highest derivative. So nonlinear second order PDE. Good. And then we have another term called the homogeneous equation. Okay, so homogeneous equation. So what's a homogeneous equation? Homogeneous equation means there is no term of the independent variable only. Okay, then you call it homogeneous. No term of the independent variable, independent variable alone. Okay, so no term of the independent variable alone. And then this equation can be written in this form. So this can be written in the form. So this can be written as anx d squared, not d squared, dn. So here is this. dn y over dxn, like that, and then we have a1x dy over dx plus a0 x y equal 0. So that's the important part. You have a 0 there. Okay, so you can see that there is no x term. X is the independent variable. There is no x term on the other side. Okay, so it simply means that bx is identical to 0. So it's gone. Okay, so any homogeneous equation you can write it in this form. So what you're going to do is you set, once you take all the y terms to one side, you have only 0 on the other side. Okay, once you take all the y terms to one side, you have just 0. Okay, so no term of independent variable alone. Good. So otherwise, if this is not the case, we call this non-homogeneous. Okay, or inhomogeneous. So otherwise they are called non-homogeneous. Okay, non-homogeneous or inhomogeneous. Okay, non-homogeneous or inhomogeneous. Just two words. So we normally call non-homogeneous most of the time, but even if you hear inhomogeneous, it's the same thing. Okay? Non-homogeneous or inhomogeneous. So let's look at what homogeneous equations we had. So some examples. So we had several examples. For example, the exponential growth and decay. So exponential growth or decay, and then the wave equation, and the transport equation. are all homogeneous. They are all homogeneous. So that's a good idea to check. Okay, so check whether they are actually homogeneous, whether there is no term of the independent variable along. Remember, constant, let's say if you see a constant, that is a function of the independent variable. It's a constant function, so be careful with that. The mechanical vibration, okay, mechanical vibration is non-homogeneous. The mechanical vibration is non-homogeneous as long as ft is not identically 0. Ft is not identically 0. Identically 0. Identical 0 means 0, okay, just a 0 function. So otherwise, if ft is not equal to 0, it is non-homogeneous. If ft equal to 0, it is homogeneous. Homogeneous equations are easy to solve. Okay, this one. So the next type is what we call constant coefficient equations. Constant coefficient. Okay. Constant coefficient equations. So what we say, the constant, it says everything. I say the constant functions are coefficient functions are constants. Okay, so coefficient functions are constants. Okay, coefficient functions are constants. So we can spend a lot of time for that type of one because those are the easy types. And then can be written as an dny over dxn plus a1 dy over dx plus a naught y equal bx. So you can write all this one. You can see that an, a1, an through a naught all are constants. Okay, so a naught, a1 all the way up to an are constants. And bx can be a function, can be non-constant. Okay, can be any functions. Okay, any function of x. So that's okay. So these type of ones are what we call constant coefficient, and we're going to spend a lot of time for these type of equations. Okay, a lot of time, more than a month. Okay, so let's look at some examples of constant coefficient equations. So let's see some examples. Example 1. So it is 2d squared y over d dx squared minus dy over dx plus, so you can see y equals 0. So this is a constant coefficient homogeneous, right? So this is constant coefficient homogeneous. Constant coefficient homogeneous equation. Why homogeneous? There's a 0 in here. So, and then how about this one? 2 d squared y over dx squared minus dy over dx plus y. See, you can see that all the coefficient 2, negative 1, 1, they are all constant, equal sine x. This is constant coefficient non-homogeneous. Constant coefficient non-homogeneous. Okay, we can solve all of these. Okay, we can solve them later. And then two other cases, we have the mechanical vibration. Mechanical vibration equation. What can I say about the mechanical vibration equation? You can see it is a constant coefficient, non-homogeneous in general, constant coefficient non-homogeneous, second order ODE. So that's like a major classification. You can say constant coefficient non-homogeneous, second order ODE. Yeah, and then we can solve that also later. And then we have the transport. So transport, heat, and the wave. Or you can say constant coefficient. So all constant coefficient linear PDEs. Okay, constant coefficient linear PDEs, linear. And the mechanical vibration is also linear because there was no any product terms there. Linear. Okay, so the last type, autonomous. Autonomous equations. So what does autonomous means? Autonomous means the function does not depend, differential equation does not depend on the independent variable. Okay, so the equation or the system, equation or the system is called autonomous if the equation does not depend on the independent variable. Does not depend on the independent variable. So most of the time this independent variable is time. Okay, most of the time it is the time variable. So that means, in other words, it says that, so we can say it does not depend on time. Okay, it's fixed. Okay, so if you have a different time, the differential equation is still the same. So it means, so an example, Newton's law of cooling. Okay, Newton's law of cooling is okay, Newton's law of cooling is autonomous. Because it does not depend on the time variable. There's no t term on anywhere, okay, except the derivative. And then the mechanical vibration is not. Mechanical vibration is non-autonomous. Non-autonomous. This is autonomous, non-autonomous, because you can see in the mechanical vibration there's a ft term. That means difference equation change because of that. So since there is ft. That's the reason. Okay, so this is about the classification, and then you can see that we talk about several different type of terms here. So we talk about what we mean by a ODE, what we mean by a PDE, and then we talk about what we mean by linear, nonlinear, and then we talk about constant coefficient, and then homogeneous, and then we also talk about constant coefficient equations, and then also autonomous differential equations. So there are a lot of different types, and then we also talk about how you can figure out whether it's a how you can kind of classify into those types. Okay, so so that is the end of the classification of differential equation lecture.